A new chapter, probably the last one of these classes. It's chapter 7, Heaps and physics, mainly statistical mechanics, statistical physics. So a few words about statistical mechanics if you don't know anything about physics and statistical mechanics. So it's to have a modelization of what is called critical phenomena or phase transition. For example, when water is boiling, it goes suddenly from liquid, you heat the liquid, and suddenly it becomes a gas. So there is a phase transition. Suddenly, or if you put too much pressure on somebody, pressure, then suddenly it's going to break down and collapse. This is a kind of phase transition. Even I am a winemaker, and in the vineyard, in middle of August, there is a phase transition because suddenly all the sugar which the plants get in all the roots everywhere go suddenly into the grapes. So the grapes become from green to dark to red, become suddenly a few days, half of the sugar get in a few days. So this is a critical phenomena. And we want to understand. To understand means to make a mathematical modelization of this. So the mathematical modelization is we are going to take a lattice, and there is local interaction. It's a discrete modelization. There is some local interaction. And from this local interaction, then we want to conclude the global behavior. Like you have a modelization of water or a gas with atom, and then suddenly the water is boiling. So it's a consequence of the modelization at the local level. Typical model in statistical mechanics, the Ising model. I should say Ising model. Ising is a German man, but so we should say Ising, but he escaped from the German Nazi government and he go to the States, and he was so shameful of his. So he said, "Give my name like American pronunciation, Ising, and not Ising." And so he solved this famous Ising model. He solved it. It's a model for magnetization. When you have a magnet, then suddenly, if you hit the magnet, then it's going to lose magnetization, or the magnet is going in one paper. Yeah, yeah. Done this in one paper. He solved the model in '94, and then there was many other model, exactly solved model, which is a book by Baxter on exactly solved model. So there is some philosophical discussion if this exactly solved model are exactly the model for natural phenomena. Because you have to simplify a lot of hypotheses to be able to solve, explicitly solve, give a genetic function. But the fact is that an argument for exactly solved model is that the behavior of this exactly solved model is the same as the behavior of natural phenomena. Even if it's a very simple model, not so simple. It's simple enough to be solvable, but not too much to behave like the natural phenomena. So typically in statistical mechanics, you have a function, f of t, thermodynamical function, which depends on the temperature. And then this function has a singularity somewhere, the critical temperature, like when the water is boiling. When t go to t index c, the critical temperature, then this function becomes infinite. So this is a phase transition. And then the behavior of the function near the critical point is measured by a critical exponent. Alpha is called in physics critical exponent. And you can measure this in natural phenomena. So physicists say that different models are in the same university class. It means they have the same critical exponent. For example, we are going to work on the triangular lattice, square lattice, or hexagonal lattice. Maybe the critical temperature will change, but not the critical exponent will be the same in different lattices. So example 1, the Ising model. So you take a rectangle on the square lattice, a part of the square lattice, rectangle m by n, and each vertex have two colors, blue or red, which means it's a spin up or spin down. The magnetization, it's when all the spin are up, then you have a global behavior which becomes magnetization of the magnet. If there is a random distribution of blue and red, means there is no magnetization. So typically, you have to you have to count such configuration. In fact, the explicit physics model is there is an interaction if you take two neighbor vertex, sigma I, sigma j. Then one of them is a plus, or one of them is a minus, or blue, 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 red, red, blue, or red, red. Then there is an interaction between the two, some energy. So the physicists call this total energy of the configuration. It's the sum of a whole pair of adjacent vertices. That means usually the only next neighbor have an interaction. If you are too far from each other, then there is not at all any interaction. So there's a kind of energy between each neighbor adjacent vertices, and the coefficient J is positive or negative if you have ferromagnetism or anti-ferromagnetism. And then the physicists, to solve the model, they introduce a function. It's called the partition function. So the partition function is the sum of all possible configuration. So configuration means that it's all such, you fix the rectangle, you take all configuration, it's 2 power, the total number of vertices of the rectangle. For each configuration, there is a certain energy, total sum of all the energy of all adjacent pair of vertices. And so you get this partition function for the finite domain. It's a sum of all configuration of this. This is classical in physics with the Boltzmann constant. There is a temperature. And in fact, you don't need to understand all this physics. We can reduce the problem to a commutative problem. By reducing this, this can be expressed like this. And then I have a certain weight, which depends of the magnetic field, or no, which depends of the energy. H, I think, is equal to J. And what you have to remember is that this is a generating function of closed subgraph. What means this? So you have certain generating function. This is closed subgraph if this. See, I transform this configuration into this one. So closed subgraph means that you have a certain subgraph of the grid, finite grid, where every vertex there is 0, 2, or 4 edges on every vertex. So this region, see, if you take the blue region and the red region, then they are separated by this kind of lines. You put, for example, you put red inside here, then you will put blue here, red. So this is a delimitation, the separation of the blue region and the grid and the red region. And so the partition function, which was defined like this, for each total sum of all configuration, this partition function becomes exactly this. It's a generating function for closed subgraph by the number of edges, and then you replace each edges is going to be a certain weight, which depends of the energy parameters. What you have to remember is that the Ising problem is exactly to count such closed, what they call closed subgraph. You have to count for a finite domain how many such subgraphs. But in fact, this is not the end of the story, because what we want to do is to have a very large lattice. So this is the so-called to go to the thermodynamic limit. So what means the thermodynamic limit? Intuitively, you take the partition function and you want to get it for the infinite lattice. It doesn't make sense if you take this such a configuration on an infinite lattice, but it makes sense if you take this partition function for a finite rectangle m by n, then you take the power 1 over capital N. N is the total number, capital N is the total number of points of the rectangle. So you take the power, the partition function for the finite rectangle, power 1 over the number of points, which is m multiplied by n. And then you take the limit in a certain way. I will explain what it means when we'll translate the problem into combinatorics. So it's the first finite domain. Then you have a certain energy configuration which become to take the sum of the weight of all some finite configuration. So it's a counting problem, enumerative problem. And then the big problem is to take the limit, the thermodynamic limit. So what it means to take the limit, see if the domain is this instead of rectangle, what it means to take the domain going to infinity. Usually the thesis, they say, okay, we take the rectangle going to infinity in one dimension, for example, the length, and then going to infinity to the second dimension, and we suppose the two limits can interchange. But they don't prove this, usually. Or a torus, yes. Yes, it's better on a torus, but... So we'll make, by translating everything in combinatorics with Heaps, we will make a precise definition what means the limit of the domain. So second example. This we will treat in the class also. A gas model. Gas model means, this is a famous gas model. We take the triangular lattice. Every vertex has 6 neighbors, a 6 triangle. It's colorable with 3 colors, blue, red, and green. You take a domain, D, any finite portion of the lattice. And then you take some, you suppose it is a gas. A gas means there is some point. This is the element of the gas. This is the atom of the gas in black, such that there is no two black points are adjacent. So it's a gas with interaction. Interaction means they don't like each other. You don't put 2 black points on adjacent vertices. So in graph theory, this is independent set. In Heaps theory, this is trivial heaps of pieces. No 2 vertex are adjacent. Also, I can put like this. Each vertex, I put an hexagon, and you have to, the partition function of this gas model, the partition function, for a finite domain D, how many ways you can put hexagon 2 by 2 disjoint on this domain D. So which means it's a polynomial, the generating function of trivial heaps of pieces. So we are in familiar ground, and even you put a minus t, this is more beautiful. And then what means the thermodynamical limit? It means you are going to take the limit. So this is a polynomial. A, n, and d means the number of ways to put n hexagon 2 by 2 disjoint inside the domain D. And then you take the limit of this polynomial, power 1 over the number of elements of the domain. So this is going to be a formal power series. And we suppose that it makes sense to take the limit, and the limit exists for a certain way. Or usually domain is a rectangle. You go the rectangle to infinity, first in one dimension, and then in second dimension, and you suppose the 2 limits commute. And this is a famous hard hexagonal Baxter model. He find this was one of the best achievements of Baxter, Ron Baxter in Canberra in Australia, and he find an explicit solution of Z of D. This is very beautiful solution, very difficult, very deep solution. It involves, this is the big surprise, it involves the famous Roger-Ramanujan identities in the solution. And so we will try to explain this by combinatorics of Heaps. So this gas model, in fact, between 2 points, there is an interaction. If you have 2 points which are neighbors, there is an energy interaction. And this gas model, to say that 2 points are not adjacent, it's a limit of the general gas model where there is some parameter. It's a limit case, but this is a very, very famous. So I just want to show you that there is a phase transition. If the domain is very big and there is very few hexagons, you say you have colors, the domain in 3 colors, blue, red, and green. So this hexagon is red, at the center is a red point, this hexagon is green, this hexagon is blue. And then you can ask, if the domain is very big, there's very few hexagons, what is the probability, if I take a random hexagon, to be blue, red, or green? And it's about 1 over 3. Each hexagon will appear with the same probability if we are in a gas. Now the extreme, if you packed all hexagon, then there must be all hexagon red or all hexagon blue. Like this or like this, you see. So if you start from a very compact configuration and you delete a few hexagons, then the probability to get a red hexagon is very high. It's almost, now it's 1, and then if you delete some hexagon, it's going to be close to 1. And if you delete many, many hexagons so that you come back to the gas, then probability will be 1/3. So between the two, there is a phase transition. And the phase transition appears, it is very beautiful, at the temperature, it's at the golden number power 5. The golden number is here behind this phase transition. And there is a critical exponent, which is 5/6. And there was some experiment on helium, liquid helium on the two-dimensional plate. And they measure the critical exponent, which is close to 5/6. And this 5/6 comes from the solution with the Roger-Hammond-Lejeune identities. So it's a beautiful mixture between the real world and beautiful model in physics. Yes? Three colors, yes, here. No, only three colors. It's why to color more color? It's here. It's just to explain the phase transition. The density of the hexagon, there is a blue, red, and green. And if you color, it's more complicated. If you put you have to give a rule how to color with more than three colors. Yeah, there is a unique way.
But in other cases, it may not be unique.
If I have the square lattice, then I will put only two colors. For the square lattice, it's a bipartite graph. This is with three colors. It's just a convenient way to show to compute the density, to show the phase transition.
How do you color the vertices? So here I can see some pattern.
It's a dual.
Well, you take one of the vertex. You start with a triangle. Take a triangle, blue, green, red, and then you continue. You have a unique way to continue. So this must be green, this must be red. You start with the color. One triangle has three colors, and then you propagate the color in the whole lattice. So there is a strong relationship between combinatorics and statistical mechanics. For example, the enumeration. To enumerate this closed subgraph, enumerate this. This is before the thermodynamical limit. And usually physicists, they make a big effort to compute the partition function. For example, on Ising model, you have to compute this partition function. And then this is going to be equivalent to dimers, which is going to be Pfaffian, determinant, everything. So you have a long computation. Here, it's impossible to compute, to give an explicit expression for this polynomial. But the interest of Heaps is that instead of working before the thermodynamical limit, we are going to work after by using the logarithmic lemma. And then we are going to give an interpretation, for example, of this model. If I go after the thermodynamical limit, then I will get an interpretation in terms of pyramid, in terms of Heaps, so which is much more convenient because I am in three-dimensional. I can work with working at the floor. It's you are completely bounded by being on the floor level. But working with the Heaps, you have a much more opportunity, much more freedom to solve the problem. So after the thermodynamical limit, you will get this critical function, this thermodynamical function, and usually sometimes we are going to see today that after going through the thermodynamical limit, then this partition function is going to be a power series where an maybe is some coefficient or integer. For example, an for the gas model is going to be certain derivative function for directed animal or Heaps or polyominoes, etc. So an is counting something, which is totally different from the counting before the thermodynamical limit. For the gas model, it's for counting independent set in a finite graph. Now I am counting something completely different. And so this generating function, if I work in enumerative combinatorics, if I don't know explicit formula, then at least there is some asymptotic formula. So this is the so-called analytic combinatorics. There's a big book by Flageolet and Sedgwick on analytic combinatorics. If you don't find formula for an, at least you can find a formula for the equivalence asymptotic of an, where n is very big. And then asymptotic usually is mu power n minus theta, and there is a relationship between alpha and theta. The two critical exponents are just shifted by one. So it's equivalent to find this, it's equivalent to find theta. the mu is going to be the inverse of the critical temperature. So you see, finding this critical temperature and critical exponent is equivalent to find an asymptotic of the coefficient AN. Third and last example, percolation. Percolation, you take the grid, for example. Each vertex, a red point is going to appear with probability P. So if the probability P is very small, you get some connected component here in red. So if P is very small, then it's like a modelization of infection. You have infection spreading everywhere, and then if the infection spread not very quickly, then the probability is small. You get some finite cluster of elements.
What is P?
P is the probability in each vertex to appear, in each vertex independently, a point is going to appear with probability P. Then if P is increasing, suddenly, at a critical probability, then the whole, you will get some infinite cluster of points, which means you can cross the whole lattice by following some red point, going to the next neighbor with a red point. So which means that else your infection, if it's a disease, if the infection is limited, and suddenly the infection is spreading everywhere. So this is also a critical phenomena with a critical probability. And then you have to count to solve this problem completely explicitly. You have to count such a thing which are called animal or polyomino. This is a polyomino. It's a connected union of square, such that the interior is also connected. And if you replace each square by a point, you get an animal. Like this, you see an animal, it's a connected, it's called an animal because each point is a cell, the cells are growing. So an animal means that if you take any 2 points in the animal, you can go from one to another by a path going to the next neighbor and going north, east, west, or south. And solving completely explicitly the percolation problem is you have to count such animal by the number of points and also the number of points at the border. The cross means that if you add a new point, then it's still an animal. Or in terms of polyomino, if you prefer polyomino, you have to count such polyomino by the area, the number of squares, and the perimeter. The perimeter is the number of edges at the border of the square. So this problem is totally unsolved. To count general animal, general polyomino, this is totally open, but nobody knows. Maybe there is no formula, nothing. It's just some experimental or asymptotic result. But today there is one subclass of animal and polyomino. There is many subclasses have been enumerated. There is many beautiful formula. So there is a subclass which is called the directed animal model. So this was invented by physicists in the early 80s. It was not by combinatorists. So here is a directed animal. So directed animal means you are on the square lattice. There is the origin in red, the source point, and definition. A directed animal means that any points of the animal like this can be reached from the source point, the red point, by a path like this, going to the next neighbor, and the path is only using east, elementary east step, or north step. Maybe you can go in 2 different ways. See, you can go to my point like this also. But any point can be reached from the source point by a path going to the next neighbor, a sequence of points inside the animal. Right? It must be a sequence of points inside the animal, and from one point to another, you go to the next neighbor, east or north. So you see, general animal means you do the 4 possible steps, north, east, north, south, east, west. Here I have only 2 possible steps. I am going to the northeast. So this means directed animal means, see, there is the animal tends to grow to the northeast direction instead of growing in all possible directions. And the problem posed by physicists, I will explain the different reasons why the physicists introduce this. I finish my. The problem is to find the number of directed animals having endpoints, to find the generating function. Yes, a question?
Whether every animal is, with respect to some point, it is directed?
Directed means this.
If I select, if this animal is, with respect to some point, it is not directed.
You start from one point. which is called the source point, and all the other points can be reached from this
For
unique
example,
point.
if I take the topmost point, then
No, only this point.
no,
There is a source point. This is origin.
no.
Counting animal means I am counting them up to a translation. Or if you prefer, this is the origin of the plane, 0, 0, this point. And any point can be reached from this point.
No, what I'm saying, like if I just take an animal and I can decide one point, it's like possible to have this is a directed animal.
There is always only one point because it's the
There's only one point.
south.
Only the directed animal. There is only one source point. Only one point can be have this property because
Every animal is there a one point?
Yes. For a directed animal, yes.
Every animal.
No.
no. Are you taking a general animal or directed animal?
General animal, is there any one point we can get direction?
No. Of course, for a general animal, if you take any point, can be the source point, and all the other points can be reached by your path going in the four direction.
But if we take the
Because any pair of points must be reached from one to another by a path going in the four direction. But for directed, there is one point, the source point, only one, where all the other points can be reached from the source point. And the problem is to enumerate such. So in terms of percolation, that means there is it's related to the directed percolation. It means there is some wind in you. If you have some trees with fruit trees, with infection in the tree, there is some wind blowing in your orchard, there is some wind blowing in the forest, and the infection goes to the northeast. So here at the left, we are not infected here. It's and directed. So this problem to count the number of directed animals is directly, if I make a joke, directly related to the directed percolation. In fact, you have to count animal by the number of points plus what should be the directed perimeters. Means the number of points outside of the animal, but if you add it to the animal, it stays a directed animal. So you should count this to the two parameters. But today, it's too complicated. Let's just count by the number of points. So there was many connections at that time by physicists. There was a dozen, maybe 50 papers appear at the same time in '82 for counting these animals and counting some critical exponent. There is more than this. So you can take the size of the directed animal, the length, and the width. So this is the length. Take the smallest rectangle, the rectangle 45 degree parallel to the diagonal and perpendicular to the diagonal. So this is a rectangle, the smallest like this containing the directed animal. So this is the length of the animal, the size here, and this is the width. And physicists, they want this. What they want, maybe not explicit formula for AN, but they want to have the behavior of AN is going to be something like mu power n minus theta. So theta is a critical exponent of directed animal. And then the average width, average length, what it means average, means that you take all possible directed animal with n points, with equal probability, uniform probability, and then you take the average width, average length, and it behaves like this. So there is these three exponents are called critical exponent. And in 1982, there was a tremendous number of papers. Most of them were using phenomenological renormalization, some quantum, some techniques. I don't understand field theory, everything. But there was three physicists in Paris who gave some explicit formula for the number of directed animals. So these three physicists were Nadal, Derrida, and Veniminis. Derrida is famous because he gets the Boltzmann medal in statistical mechanics. This is the local Nobel Prize for statistical mechanics. Veniminis, Nadal also. They were younger at that time when I met them in early 80s. They were at the École Normale Laboratoire de Physique of the École Normale Supérieure. So this famous school and laboratory. And what they have done as good physicists, you apply the transition matrix method. So you put your animal in a bounded strip. And as Suresh was saying, it's better to make cyclic. So you make a circular strip, which means that this border here in blue is identified with this border on the left. So imagine your picture on a cylinder. And then they make general directed animal. So here in red, here is a source point. And definition of such animal is any point in green can be reached from one of the source points by a path going to the northeast or going to the northwest. So you see, this is this point. You see, this point as it is identified with this one, it can be reached. You see, I have a path here, starting here, going here. I am reaching this point, and this point equal to this one. So okay, I can reach. I am on a cylinder. And transition matrix means you cut your cylinder here. You are in a certain state. So if the length of the cylinder of the circle is k, so there is 2 power k possibility. And then there is a transition from one state to another state, which tell you that it is a directed animal. You cannot, there is some transition possibility. So you have a big matrix of 2 power k row and 2 power k column. You have to find the characteristic determinant polynomial, and then you have to find the eigenvalue, etc. And then and these 3 people, they guess the formula for such. They guess and they get this just by experiment and guessing. It's amazing to get this explicit formula. And you recognize here the zero of the Chebyshev polynomial. We met Chebyshev many times. And the way they get this, it was very funny, because they were working on a computer. They take, for each size k, they have the list of all the biggest eigenvalue for each size k. So we have a list of real number with a digit. And just the next neighbor was taking some zero of chromatic polynomial of some polynomial that I talk in chapter 5. It's saying the limit of the chromatic is going to be 4, which means the 4-color conjecture is almost false. So they were in both computers, and the number was exactly the same up to a shift of 1. The digit was the same. So they get explicitly these numbers, and then the rest with standard techniques, they get the whole formula. So you see, we know in real number, you can be surprised. And what means, so this formula, you see, it's what means Ni is a number of I whole. See, if you have on the circle, you have some source point, and between 2 source points, there is some high points. And Ni is the number of times you get this pattern. And all the number is sinus, cosinus, everything. So from this, they deduce that the total number of animals on a cylinder of size k is behave like this, where mu k equal this big eigenvalue, 1 plus 2 cosine. So if you go k to infinity, now you go the size of the cylinder bigger and bigger and bigger, and you get this formula with mu equals 3. And also they compute theta, and by some technique, some physicist techniques, they get the critical exponent 1 over 2. They get theta equal 1 over 2. And nu, the average length, the critical exponent, for a certain time, they conjecture it was 9 over 11. But then Deepak Dar in Mumbai, in Tata Mumbai, he showed that it was not 9 over 11. And to my knowledge, the problem is still open to find the average exponent for the length of the animal.
Why is there asymmetry?
Because you will see, I will show you a picture of random animal, random directed animal, and you will see there is the critical exponent for the width is half. Critical exponent for the length is much bigger. It's almost 1. So the animal is very, very long. So it's related. Derrida makes some study about fractal. He introduced fractal dimension, and this animal has a typical fractal behavior. But the fractal dimension in one direction is not the same as the fractal dimension in the perpendicular direction. And these 2 fractal dimensions are related to the 2 critical exponent for width and length. So it's a beautiful example where combinatorics meets a lot of other field. And then it was proved by Hakim Nadal and Deepak Dar. In fact, they find the derivative function for a directed animal. In fact, if you follow the class in the beginning, it is very simple. You can solve immediately in 3 lines this problem by using heaps of pieces. Very simple. So directed animal and heaps of pieces. So there is a bijection between directed animal on a square lattice and strict pyramid. Because if you just turn turn the directed animal on the square lattice, you put it like this, and you get a strict pyramid. Strict means, you see, there is no two dimers touching one over another, which means if there were two dimers touching, it means you are in fact in the triangular lattice. But if you are on a square lattice, the directed animal on a square lattice is in bijection with a strict pyramid.
Why is it Heaps? The rightmost Heaps and the second one, why is it?
Well, because it's, I have just turned, you see. I have just turned. And it's a pre-heap. This is a pre-heap, so this would fall down. If it's not a heap, it's a pre-heap. The dimers are floating in the space and just would fall down. In fact, we did better to turn it upside down, to put the source point below, and then you have an anti-pyramid, and then no dimers are going to move. And so you have to find the genetic function of strict pyramids. But any strict pyramid is a strict semi-pyramid plus this, which is a product. So pyramid, everything is strict. So strict pyramid is a semi-pyramid like this. Or maybe if there is more than, see, if on the left of the maximal piece there is nothing, it's a semi-pyramid. If on the left of the maximal piece there is something, then this you push, and you have a unique decomposition as a pyramid multiplied by a semi-pyramid. Everything is strict. Then I have to find the equation for semi-pyramids. So semi-pyramids is equal to, maybe it's a single dimers, maybe in the column below, at the right there is some dimers, or maybe there is some dimers at the right and some dimers below the maximal piece, so you can easily convince yourself that there is a three different cases which give you this equation for semi-pyramids. So you have an algebraic system of equations. And now the surprise is that if you look in the Sloan, in the encyclopedia of numbers, then you will see this. So you can find easily the number of directed animals with endpoints. And you will see that this is exactly the same as some numbers related to Motzkin path. So here is a Motzkin path. We have seen this last year. A Motzkin path is a path on this quarter above the zero level. You go every time to the northeast, east, or southeast. So there is some level going north, northeast, east, or southeast to the next neighbor. If there is no level, this is a Dick path, counted by Catalan number. If there is some level, this is counting by Motzkin numbers. Now, if I take the left factor, I cut my Motzkin path before finishing the last point. So it's a prefix or left factor of Motzkin path. And this prefix or left factor of Motzkin path satisfies this algebraic equation. The prefix of a Motzkin path is else the Motzkin path, or else t times the prefix multiplied m. This is a generative function for prefix of Motzkin path. M is a generative function for Motzkin path. You take the last time, you see, for you easy exercise to show this unique decomposition. Now, Motzkin path is a unique also decomposition giving you algebraic equation. So this is easy exercise from chapter 2 about generating function, the algebraic system equation, and to show that this algebraic equation is, you have just to take the first time you touch back the zero level. It's very classical. I don't insist on this. And if you compare the two equations, this equation for strict semi-pyramid, equation for left factor Motzkin path is exactly the same, just by shift of 1. So I conclude the number of directed animals with endpoints is exactly the number of prefix of Motzkin path of length n-1. So this is a beautiful problem because I have an equivalence between this two-dimensional directed animal is in fact in bijection with a one-dimensional path. Motzkin prefix of Motzkin path is just a path on this line on the one-dimensional, meaning you start from 0. At any time, if you have at level I, you go to I plus 1, you stay at I, you go back to I minus 1, and you finish at any level. So such one-dimensional paths, if you want to see them, this is expansion in the time, Motzkin path, and this is in bijection with directed animal. So with Dominique Gouillot-Beauchamp, a long time ago, we we give a direct brute force bijection without using this decomposition with Heaps. But working with Heaps, you see, it's easy. When you get the Heaps, it's easy algebraic equation for only difference there's strict pyramid instead of pyramids. There was an exercise to show that the number of pyramids of diamonds on the integer was half of 2 and 2n. So it's in bijection pyramid with bilateral dig path. Here for strict, we're in bijection with left factor of Motzkin path. So this is the same Motzkin, Catalan, all this is classical, easy, algebraic combinatorics. And now you can explicitly give the generating function for the animal, solving explicitly the system equation, and this gives you an explicit formula for the number of directed animal. Exercise, easy exercise. This is a standard routine technique to go to play from generating function to solving explicitly. And there is more than that, that if you take the width, I claim that we can get in the critical exponent of the width. If you define the lower width of a directed animal, you see, instead of defining the width, you just take this distance. Instead of taking the whole rectangle, I take the lower width. I call this the lower width. There would be an upper width, and total width is the sum of the two. But if you take the average of the width, it's going to be twice the average of the lower width. And then it's a remarkable fact that if you take the sum for all of left factor of Motzkin path, take the sum of all the lower widths, this gives you 3 power n. Again, another exercise to show that the sum of all the height of the last point of prefix of Motzkin path is exactly the sum of all this is 3 power n. So the average gives you the square root of n. So all this is easy exercise for if you want to play with generating function and factorization in Motzkin, etc. This is looks like the exercise I gave last year about Catalan, about the Catalan garden. I don't want to insist on this. I want to insist more on the physics than on the combinatorial part, which is easy to do. But from this now, from the bijection, the bijection can be put in linear time. The bijection from directed animal to left factor of Motzkin path, this single path, it's algebraic generating function. So there is some efficient algorithm to find a random prefix of a Motzkin path, which gives you a random animal. And now here is a random animal of size n. So you can really see the difference between the critical exponent of the length and the critical exponent of the width. This is another random animal. So you see, they are very, very long, very like a tree. There is very few loops in such animal. So this is you can give to your student in computer science to make the algorithm to find a random animals, and just from the picture you can immediately see if it's correct or not. Because if you find a Ferrari diagram, then Ferrari diagram is a directed animal. Compact, but there is very few. Probability to get this is a. So complement our exercise. How did we find this bijection with Guyot-Beauchamp? We have a more general animal. It's animal with a compact source directed animal. So you put all the red point consecutive on a 45-degree line like this. So it's an extension of the directed animal. There is several source points. They are all compact. Compact means they are all consecutive on a line perpendicular to the diagonal. And the definition is that any point of the animal can be reached from one of the source points by a path going east or north. So if you want to count total number of compact source size directed animal, there is one with 1 point. With 2 points, there is 3 such animal. With 3 points, there is 5 with 1 source point. There is 3 with 2 source points. And there is 1 with 3 source points. Total is 9. If you continue by experiment, you will find 1, 3, 9, 27, 81. So this was a big surprise for us, that the total number of compact source size directed animal is 3 power n. It is the most simple formula you can find in combinatorics.
2 power.
2 power something.
There is also some 2 power n plus 1 over 2. But here the more simple, 3 power n, only 2 symbol. Power, 3 symbol, 3 power n. So it's really true that it's 3 power n. This is not a factorial. So we gave a bijection. In fact, that's the way we gave the bijection for the one source point. In fact, we extend to several source points. So the bijection is to take any word in 3 letters, A, B, C, and there is a bijection which transforms this into a compact source size directed animal. So everybody say, well, we have just to prove that an plus 1 equals 3 times an. Yes, but to prove that this, it's... Or the derivative function is 1 over 1 minus 3t. So any way you try to do by calculus, you are forced to find something bijective. So we get a direct bijection, which is very complicated. It's deep, but there is a way to do it with heaps of dimers. So you see, if you take a compact source directed animal, you have a kind of pyramid. It's not a pyramid with the maximal piece are all consecutive. This is a source point. And else there is one source point, or maybe if you push all the source point, if there is more than one source point, you keep the rightmost source point and you push here, and you get this equation where capital X is generating function for compact source size directed animal, or it can be the set of animals. It's an equation in terms of the combinatorial objects themselves instead of working with generating function. And then so this was done proved by Betrema and Pedot. So if you take the 3 equations, and then you get X equal this. And more than that, if you want to have the lower width also, the width and the number. So you take for a compact source size animal, if you define again the lower width, number of source point, and then the double distribution of this animal for these 2 parameters is symmetric. It does not seem to be symmetric, but it's symmetric double distribution. And it's exactly the double distribution on this path. So this is path counted by 3 power n. You start at level 0 and you go in the 3 possible up, down, or stay same level. So here is the 3 power n. This is path with 3 possible steps. And if you take this, the minimum element, minimum level, and take the distance between this point and the minimum level, distance between the last point and the minimum level. So you get a double distribution with 2 parameters of this path counted by 3 power n, and this double distribution is exactly the same as the double distribution here. So you can conclude average width for one source size directed animal, everything. You can conclude, and there is a generating function with 3. So finding a random word with 3 letters is very easy. So you can get very quickly, very easily picture of random compact source size animal, and here are the picture. This is a random 3 power n. If you see this, you say, okay, this is 3 power n. It's a random compact size source animal. This is another random animal. So it's part of, you see, of like a random animal with a one source point, but like seed in the sea, or so we have done directed animal with a square lattice. We were a little embarrassed because you have to get strict heaps, so it was not so easy to take directly heaps. But if I take directly heaps, I am in a triangular lattice. So triangular lattice means it's the same definition, but for the directed path, any points of the animal can be reached from the source point by a path going north, going east, or maybe northeast. You allow this point northeast. So when you go to the pyramid, this means you allow to have 2 dimers, which one dimer is covering the other. So to forbid strict To have strict pyramid means you are forbidden the northeast step. This, for example, is two dimers one over another correspond exactly to this northeast step. No, to this one. And so there is a bijection between strict pyramids. No, there is a bijection between directed animal on the square lattice and pyramids of dimers on the. So we know that this from the exercise is half of 2n chosen. Yes?
If we can have an addition, so whether this will give some addition in animals also.
Addition? What means addition of heap?
We can combine the heaps one after the other.
No, the product of heaps.
Sorry.
Product.
Whether this will give a product of animals.
No, because product of pyramid, you are going to lose. It will not be no more a pyramid. So you can make product of many pyramids like this, and then there is a way to define this, and so you can define multi-directed animals. So this has been done by Reschnitzer and Mireille Bousquet-Melou. They have defined more general directed animal with several source points, but are not like a compact source point. So it's a way of defining certain product, not completely arbitrary. It can be decomposed into pyramids. And this animal, in fact, we will do it in the next chapter because they are connected to the so-called Lorentzian triangulation in quantum gravity. So it's a very beautiful connection between multi-directed animal and this quantum gravity by taking triangulation of the space-time. Usually space-time in 4 dimensions, but here to be solvable, I will do space-time in 2 dimensions, and there will be a connection between this multi-directed animal and some triangulation, which is called Lorentzian triangulation. So there is many words. We will talk more in the next session. But how to go? In fact, there is an easy way to go from strict pyramid to pyramids. If you know the generating function of strict pyramid, then there is a relation with generating function for pyramids. From strict heap to heap, you can just do this operation. Take a strict heap and replace the dimers by just a pile of dimers, which means you replace the variable t by 1 over 1 minus t. So if you take the generating function of strict pyramid, replace t by, no, it would be t over 1 minus t. Sorry, there is a mistake. You replace it by t over 1 minus t, then you get the generating function for pyramids. So in fact, it's very easy to get the generating function of pyramid. It's half of 2n chosen. If you go back this operation, you get back the generating function of left factor of Motzkin path. So with this operation, going from strict to large heaps, I can go back to the beautiful formula of Derrida, Van-Imenius, and Nadal on animal on a bounded strip. And this formula is not mysterious with what we have done in chapter 1 and 2, generating function of heaps. Because what we are doing, it's heaps on this cylinder with a condition on the minimal piece. So it's exactly the inversion formula. You have the generative function of some heaps of dimers on a cylinder with the minimal piece are fixed. So we know the denominator is a trivial heaps of dimers. It's a Lucas polynomial. We have seen this in previous chapter. We know the numerator is the product. You see, you have to put some the product of all this polynomial. It's a matching polynomial of this segment. Between each blue point, source point, you cut all the blue point. So you have many segments. So you have, if you call ni the number of such I hole, here it's I hole. So number of segments of size I, there is ni like this. So n is going to be the product of all this Fibonacci polynomial, and the number of times I will appear, it will be the capital N index I. So you get back this formula. You see how to get back this formula. You have a rational fraction, and we know the general theorem on rational fraction. You can expand it explicitly in terms of the zero of the denominator, but we know the denominator in Fibonacci is related to Chebyshev. So the zero, we know them. It's a denominator is a Lucas polynomial is a reciprocal of the Chebyshev up to a chance variable. So we know the zero. So we can completely reprove this formula. You have to do two things. First, the general inversion formula. So you will get heaps of dimers on a cylinder, but here the condition for this formula is to be strict. Okay, to be strict, you have to change T to go back from T to T over 1 minus T, to go back from large heap to strict heaps, and then apply the classical formula for expanding a rational fraction in the explicit term of the zero of the denominator, and this is classical things on rational fraction, and you can get back the formula. So no problem, you see. Unless just some calculus, you have to be expert in expanding a rational fraction in terms of explicit formula, like the Fibonacci numbers can be expanded with a ratio 1 plus square root of 5, etc. It's classical theorem I did not give in the class, but when you have a rational fraction, then explicit coefficient can be explicitly written as a sum of power, or maybe there is multiple roots of the denominator, sum of power of the inverse of the root of the denominator. And here we have with Chebyshev, first kind, second kind, in the numerator and denominator. So everything can be explicitly done, and have this nice formula. So now it's time to really understand the thermodynamical limit in the case of the most simple case, first the one-dimensional gas model, and then after the two-dimensional gas model with a hard hexagon model. So we have the partition function. In the one-dimensional gas model, you take a segment, and you take the partition function. It's a polynomial enumerating configuration of points which are not two consecutive points, are not 2 points of the gas are not connected by an edge. So the gas model is explicitly the partition function, in fact, trivial heaps of pieces. So it's a Fibonacci polynomial. How many way you can, if you take a segment, how many points you can put so that no 2 points are connected by an edge. It's exactly the Fibonacci polynomial. So it's very simple, one-dimensional gas model. In that case, we have to take the thermodynamical limit. So you have to take this Fibonacci polynomial, power 1 over n. And you have to take the limit of this, then means the segment is going to infinity. So to take a polynomial power 1 over n, the only way to do this combinatorially is to take the logarithm. So the logarithm of the partition function power 1 over n is 1 over n logarithm of Zn. Logarithm of the Fibonacci polynomial. But working at the floor level, I say, is not good. So why not to take the inverse? Inverse of the n is going to be Heaps. But logarithm of the inverse is minus the logarithm. So this is exactly equal to minus 1 over n logarithm of the partition, inverse of the partition function. Now we are in the logarithmic lemma. Let's take the logarithmic derivative. And then, so you get this. Logarithmic derivative of this is going to be 1 over n, the generating function of pyramids of points or pyramid of diamonds. It depends if you think in terms of points, vertices above a graph, or pyramid of diamonds. It's the same. And so you have to find the generating function of all the pyramids you can do on a finite segment, and multiply by 1 over n means you take the average. See, there are many pyramids. Depends on where you put the maximal piece. So in fact, I'm decomposing my derivative function of pyramids as the sum over all pyramids, which the maximal piece is projecting on the vertex I. So for each vertex, you have a certain generating of pyramids. And what you have to do, you see, it's take the average of all these generating functions. And take the limit. This is exactly the thermodynamical limit. And so you feel that taking the average of all these pyramids when n go to infinity, let's fix a k, and let's take the first term for each pyramid which a maximal piece projecting on the vertex I. So take this generative function, which depends on 3 parameters, I, n, and k. You take the first k term in the generating function, you limit to k, the first k term of this generating function of the pyramids on the segment of length n, which maximal piece going to I. let's fix, you fix k. Fix, and then I'm going to go to infinity. Then I claim that for any I between k and n minus k, so for any I between this and this, in this portion, then this derivative function of the pyramid, no, it should be this term, pyramid index I, n, and k, that should be a k here. The first part of the k element of this derivative function, so this monomial here, depend I and k, does not depend of I. It's because if you take any pyramid here, you see, the worst you can do is to have diamonds, only one diamond. You try to reach the border. But if you are inside this zone, then the first k term does not depend of I, because you are not going to touch this part of the pyramid with at most k diamonds. You are not going to touch the border. So in all this zone here, all the pyramids have the same first term of degree k. So you can imagine when k is fixed and n go to infinity. So what happens when n go to infinity? So this derivative function of pyramids and on n and k, what is pyramid n and k? It's the first term, pyramid nk, it's the first term of degree k of all the pyramids on the segment of length n. So this is exactly equal to n minus, so this is a fixed term, which doesn't depend of I, plus the remaining part of the pyramid which touch the border. So there is a border effect. You see, when you are close to the border, there's a border effect, but when you are between all this big zone, then there is no border effect, which gives you this fixed term. So now if you divide by n, the average of all 1 over n of all this is going to be equal to this, plus 1 over n of this. And when n go to infinity, for k fixed, this go to 1, and this go to 0. So this is the morality of the thermodynamical limit, you see. I am taking the average derivative function of all the pyramids, but if I fix the pyramid of size at most k, then the border effect will less and less important as soon as the segment becomes greater and greater. There is a small border effect, but in the bulk of the segment, all the pyramid, all the first term will be the same. So the average of all the derivative functions will be explicitly the derivative function when there is no border. Which means, so if you take the rho n, t times the logarithmic derivative of this partition function Zn, and rho for the general, this is when I go to the thermodynamical limit. If I have a gas model, this is called the density of the gas. And then proposition, this derivative function has a limit, which is this one. Limit means that for any k, the coefficient of this derivative function is going to be turned to the coefficient of this one. So limit means that the coefficients are moving, but if you take a certain coefficient, the coefficient of t power k is going to have a limit which is the same as the coefficient of t power k here. So it is a way to understand the thermodynamical limit combinatorially, properly, you see, to see what happens. You have to find when you limit your domain, you have to find the average of all the derivative function of all the pyramids with maximal piece projected on I, and this average, the border effect is going to disappear slowly when n go to infinity, and what happens is going to be this average is exactly the derivative function of pyramid when there is no condition on the border. And so this is called the density of the gas. Rho is called the density of the gas in gas model, and in physics, that's exactly what they define. So it's very good for us because this is a partition function, and then define this t times the logarithmic derivative of z is rho of t. So we need this combinatorially, and we need this from the physics point of view. It gives you the density, t sometimes called activity, maybe there is some other name. Suresh, I am correct?
Yeah, the thing is log t
log t will be the fugacity. Fugacity, and in some book I read activity is activity, or fugacity, the same, I don't know. And so I claim that minus rho minus t is the generating function of pyramids on Z up to translation. And so we know that pyramid is this, equal to this generating function. So you get explicitly, you see, the limit. You have an interpretation before the limit, which was Fibonacci polynomial. But after the limit, you have another interpretation, which is pyramid of dimers, which is really different from the Fibonacci polynomial. So, for example, the Ising model, when you always work at the floor level, in the rectangle, you have to find explicit expression for this closed graph, which is very difficult. You have to find a function, then take the limit of this. And so the idea of taking the inverse, taking the logarithm, and taking pyramid or taking heaps, this has been applied by a student in Helmut, in a student. He has applied it to Ising model and to have beautiful solution by using pyramids of paths and oriented loops, everything. It's a beautiful paper, giving this idea that you have a commutative interpretation after the thermodynamical limit, using heaps of PC, taking the logarithm inverse, taking the log of the inverse, it's minus the log, and give you heaps instead of staying at trivial heaps.
Why is it the generating function of pyramids on Z? I mean, why is it up to translation?
When I take pyramids, or you can fix the maximal piece to be 0, 1, or any pyramids up to translation, it's the same.
You're fixing the maximal piece.
Yes, I fix the maximal piece. Or if I don't fix the maximal piece, then it's any pyramid up to a translation. Or you can fix the maximal piece to be 0, 1. So this is why there is a half. Because if you fix the maximal piece to be 0, 1, then this is going to be in bijection with what we have called bilateral dick words, starting with the northeast step. So this is half of the total number of bilateral dick words. Because if you apply the bijection from a pyramid, from a path, if you take a bilateral dick word going like this, and starting to the right, then you get a heaps of dimers, heaps of cycle of length 2, and then you get a pyramid. So this was one of the exercises. There was 3 exercises showing that pyramids of dimers were exactly half of 20,000, and the 3 exercises was different method, giving exactly the same formula. So here we have the generating function. And in fact, pyramids of dimers are exactly the directed animal. The number of directed animal on the triangular lattice is exactly the density of the gas model in 1 dimension. So you have a connection between gas model, the density, and the directed animal in 2 dimensions. So this was done by Deepak Dar a long time ago, where he shows the equivalence between directed animal model with hard gas model in relation with a crystal gross model, stochastic lattice gas. So this is a very interesting paper. There is more than what I have said about the connection between pyramids, density, and lattice.
It's between bilateral liquids and
So
directed animals.
the bijection is between pyramids.
Directed animals and triangles.
No, this is pyramids of dimers. We know pyramid is exactly the same as directed animal. And pyramid is the density of a gas in 1 dimension. So you have this connection. We have a gas model in 1 dimension. The density becomes interpreted by pyramid of dimers or bilateral dick path. And this is the same as directed animal on a triangular lattice. And there is much more in paper by Deepak Dar in the 1982. In the beginning, he solved also the directed animal problem by relating it to a gas model problem and many other beautiful things. So now there is a kind of problem. If I take the partition function, if I start with the pyramids and logarithmic lemma, applying logarithmic lemma with the exponential generating function. So you take label pyramids. Remember the logarithmic lemma? It was the interpretation with label pyramid. You put some label on the heaps. 1, 2, 3, you work with exponential generating function. And pyramid, the logarithm was a generative function for label pyramid with the M condition. The minimum label is at the top, is the smallest element of the pyramid. And then, so which first problem? Look, take this. So we know that rho of t is a derivative function of pyramids. It's half of 2n choose n. So if you want to go back to z now, amazingly, z is going to be this. The partition function for the one-dimensional model is going to be the Catalan number with some alternating sign. It's not exactly but it's close to the derivative function of Catalan number. Of course, by calculus, if you take the logarithmic derivative, you will get back the derivative function of pyramid or bilateral decoys. But let's go do it the reverse in a commutative way. So you have to take assembly of label pyramids up to translation satisfying condition M, which means you take many pyramids, different pyramids. An assembly means there is no order in the pyramids. You put some label by random 1, 2, 3, 4, 5 till n, if there is n diamonds in all the pyramids, such that each pyramid get the label of the maximal piece is the smallest of the label of the pyramid. So all this together, the number of such assembly of pyramids must be the Catalan number multiplied by n factorial. I am working with in exponential derivative function. I am referring to the proof of the logarithmic lemma with exponential derivative function. So let's check. One diamond, one. Assembly of with two diamonds. So else you can take one pyramid, or else two pyramids. And remember, you put some label. So you put 1 and 2. There is only one way. Here I put some label, 1 and 2, but the minimum label may be on the top. So here I put 1, here I put 2. There is only one way of labeling. There is 3 pyramids like this. 3 plus 1 equals 4, which is 2 multiplied by 2, which is Catalan C2 multiplied by 2 factorial. Well, it's not convincing. This let's do further. So, okay, with 3 diamonds. So there is 10, 2 and choose 2 is 6 choose 2 is 20 divided by 2. This means 10 pyramids with 3 diamonds. So this makes this. So assembly of pyramids, there is with one pyramid, there is 10 such pyramids, and how many labeling? You put the minimum label on the top, so now I have 2, for the 2 other label, I have 2 possible ways. So which means I have 20 possible assembly of label pyramid satisfying condition M with only one pyramid. No, with 2 elements, 2 pyramids. So here there is 3 pyramids with 2 diamonds. Here there is 3 different ways to label this. When I put the label here, then there is one way to put here the 2 remaining labels. So this makes the total 9 plus an assembly with 3 pyramids only reduced to 1 diamond. So there is only one possible labeling. So 20 plus 9 plus 1 equals 30. 30 is 5 by 6, which is Catalan C3 multiplied by 6 factorial. So this must be true in general. So Richard's problem give a direct proof without using the derivative function with taking the logarithm, derivative, etc., going from the derivative function of pyramids to chosen bilateral equation to the derivative function with modified sign. Try to find a direct proof of this. Okay, we'll finish now with a gas model in 2 dimensions. The 1-dimensional for us to prepare you to go to the hard hexagonal model. So the gas in 2 dimensions. So I take the triangular lattice. I go back to my triangular lattice with 2 colors. I take a finite domain, and then I define the polynomial enumerating trivial heaps of points, or which mean independent set of this portion of the graph, which means how many ways you can put n points such that no 2 points are adjacent. So again, I say this is a limit case of a gas model where there is really an interaction between 2 points. There's an energy, and when the parameter go to, there is 2 parameters. When one go to 0, 0 dot infinity, I get this special case, which is very interesting limit case of gas model. So you have to find this polynomial. How many ways you can put n hexagon on this domain? So I have a certain polynomial enumerating number of ways to put n hexagon 2 by 2 disjoint on the hexagonal lattice. And then I take the thermodynamical limit. And I claim again that proposition, the density of the gas, rho of t, is interpreted by minus rho of minus t, is a sum derivative function, an. An is the number of pyramids of the triangular lattice with n hexagon. So I have analog proof as a one-dimensional gas model to understand what is the thermodynamical limit. So pyramids, say pyramid means we are putting hexagon, pyramids of hexagon, and such as that. Pyramid means you see only one hexagon on the top, and a few words of French, pyramid hexagon. It means you see only one hexagon on the top of the heap. This is a pyramid, and I claim that the derivative function of such pyramid is exactly the density of the gas model of Baxter. I have the same connection with directed animal. If you put the pyramid like this, say just turn the pyramid so that this vertical becomes the diagonal 1, 1, 1 here. So each point, you can define directed animal in three-dimensional, where all the possible steps are allowed. You can go in three directions, and you can go the blue, the diagonal, or the super diagonal 1, 1, 1. So each point of this, imagine such directed animal in the space, and each point is associated with an hexagon, and you get a pyramid, so that the maximal piece is going to be exactly the source point of the... So counting directed animal in three dimensions is the same as counting pyramid of hexagon, is the same as solving the hard hexagonal model. And this is a derivative function for pyramid of hexagon. See, there is one with one hexagon. There's 7 with a 7 hexagon, because you can put the 2 hexagon 1 over 1, or 6 possible ways to overlap with 2 triangles. Then there is 58, etc., etc. So the commutative understanding of the thermodynamical limit is the same as a one-dimensional gas model. You see, you take what you have to take. It's I just give an idea of the proof. Is take a finite domain, take the P of index D and S, the derivative function for pyramid, with the projection are inside the domain D, and the maximal piece projects on the vertex S. And then taking the logarithm of the partition function, but taking the minus logarithm of the inverse of partition function, and changing t in 1 minus t, so I get the logarithmic lemma. I have heaps of hexagon. Taking the logarithmic lemma means I'm taking pyramid, and then taking the logarithm of this is going to be 1 over the number of points. So I have to do 1 over the number of points of the domain, sigma over all possible pyramid with maximal piece projected in S. So it's going to be exactly this, taking a classical way, it's as before. And now I have to analog of my K, my segment K, where I have to cancel the border effect. I have analog in 2 dimensions now. So let's define this domain here, D index K, in this purple domain near the border of D, is all the points such that the smallest length of the path on the lattice to go from S to the outside of D. You take this smallest length, and you take the domain, all the points, so that the smallest length is less or equal to K. Which means you take all the points, which you can reach the border by taking a path with K step. So inside, you see all this. If you are any point here, you cannot reach the border with you need more than K step. So which means that all the pyramids of hexagon inside this blue domain, having less than K hexagon, they are not affected by the border. And again, the same idea, when you go to the limit will be explicitly in the sense that each coefficient tends to the limit of the pyramid of hexagon with no border. It will work to the condition that the total number of points in this border divided by total number of points of D is going to tend to 0. So suppose you have a sequence of domain such that this border condition, D and K, this number of points here, the number of points of this, divided by total number of points tend to 0. Right? So the area of this border here is divided by total number of points is going to 0. And then I claim that my average derivative function for all pyramid will limit to the derivative function of pyramids with no condition on the border. This limit means that each coefficient go to the turn to the as a limit to the coefficient of the pyramid. So see, eliminating the border condition. Now we have a precise term. What means to take the thermodynamical limit? It means as soon as your domain satisfies this condition, that the area of decay divided by area of D go to 0, then you are sure that there is a limit. So in Baxter's solution of the hard hexagonal model, he takes a rectangle, he uses corner transition matrix, and then he makes the limit, the two limits in one side and the other side, and he supposes that the two limits commute. He did not prove it, but here is a precise sense what means to take a limit. If even the domain is not a rectangle, it's any kind of domain with curvature, etc. This gives you an understanding on what is a thermodynamical limit. And to finish this introduction to statistical mechanics, I will give the beautiful solution of the hard hexagon model of Baxter. So the solution is the following. First, you have to invoke Ramanujan. That was a surprise that Ramanujan was inside this pyramid of hexagon. It's everywhere, even in the pyramid of hexagon. So you take the first two identity of Ramanujan. This is the identity relating partition. This is D partition. We have done some exercise on D partition, and this is partition with part equal to 1 and 4 modulo 5, or partition of integer equal to part 2 and 3 modulo 5. And you are going to take the left-hand side or the right-hand side of the two identity, and you take the quotient of the two, of the left-hand side and right-hand side, and you write this as a continuous fraction. I will prove it next time that completely bijectively with elementary heaps. This is n over d. This is the inversion lemma, and I will show you that this gives this continuous fraction. So this is the famous Ramanujan continuous fraction. If you put q equal 1, you get the golden number. So here the golden number is appearing. It's going to be the critical temperature of the gas, but power 5, golden number power 5. So we have to wait. White is power 5 of the golden number. So, these two identities, I call them the left hand side R1 and R2, the left, or the right hand side as you want. So taking the ratio of the two left hand side, the right hand side, they give you this Roger-Ramanujan continuous fraction. So I take R2 divided by R1, or written as infinite product, R of Q. Now you put T equal minus Q power this continuous fraction power 5. So for Q equal 1, this will give you the golden number power 5. Now write this beautiful expression y of Q equals this beautiful infinite product divided by this beautiful infinite product.
What is y of q?
Well, I just state this. Y of Q equals this. I pose T equals this. R of Q, it was well defined from the Roger-Ramanujan identity. T is defined by this. Y of Q is defined by this. Now I can define Z of T to be Y of Q of T. So you have to imagine that between T and Y, you see, you eliminate Q by your mind. Your mind try to eliminate Q, and you get Z function of T. Beautiful, huh? And this is the partition function of the gas. Z as a function of T. So you have Y here. Replace Q, take the reciprocal of this. Q is going to be a function of T. Replace Q in this. Q will be a function of T. Q is here. Q, reciprocal of it. Q is a function of T. Replace Q here. And you get Z of T, which is exactly the partition function. Amazing. Huh? So the critical temperature is going to be this. You can find the critical, from this expression, you can find the critical exponent. You can find the critical temperature is 1, is the golden number power 5. You can find the critical exponent, 5 over 6. critical temperature is a Golden number power 5, and this was already known in the literature. It was critical temperature was this, and it was conjecture. It was given by this, which is exactly the Golden number power 5. And I mentioned some experiment with helium monolayer absorbed on a graphic surface, where it seems the critical experiment seems to be also close to 5/6, which means that you see you have a model which is very simplification of gas model, but which behave analogous to some natural phenomena, but it's only two-dimensional phenomena. But helium on a graphic surface is almost two-dimensional if it's very thin. And I will finish and conclude with a research problem. It's we have this derivative function of pyramid of hexagon. So from the system of equation with involving the Q series and Ramanujan, it's possible to show, the physicists have done this, or mathematicians also in TI Fair and Bombay have done this, that they have explicit, they prove that the derivative function of pyramid of hexagon is algebraic derivative function. So, big problem since I have been working since 30 years, so this is very, I don't know, I have no idea. First idea was to use Heaps, but you need another second idea to prove that a direct combinatorial explanation of this is algebraic. Derivative function of pyramids is algebraic derivative function. And it should be interesting to find a bijective proof of this, because if you take the square lattice, so you have hard square instead of hard hexagon, if you take the square lattice, then the solution of Baxter does not work. Because Baxter he put two parameters on the solution of the gas model, and if the two parameters satisfy, there is some corner transfer matrix, and suppose they commute, so there is a certain relationship between the two parameters, and the two parameters are inside a certain quadratic surface, there are some conditions, and if you go the limit to get the hard hexagonal Baxter model, then at the limit, the two parameters are on this surface, on this manifold where the problem is solvable. But if you take the hard square model, it's another limit, and then you are outside of the manifold where the problem is solvable. So there is no way to solve it, the hard hexagonal model. So the problem is to take pyramids on the square lattice. Is it algebraic? You can take pyramid, it will be the density of the hard hexagonal model. Is it still algebraic? It seems to be, even by experiment, I give this to some young people, and they have not enough term to test if it was algebraic derivative function. So to my knowledge, we don't know. And also, if you take, again, the assembly of label pyramid of hexagon, the same as for the one-dimensional problem which give you Catalan number, if you take, then the z it's supposed to be integer here. But it doesn't mean, I learned from physicists that even if your first value of the partition function seems to be integer, it doesn't mean it's integer always. Maybe at a term number degree 10, it will be rational numbers. So yeah, problem is it integer, and what is interpretation? In terms of assembly of label pyramid of hexagon, is it divisible by n factorial? I don't know, I have no idea. It's much more complicated than the assembly of pyramid for the one-dimensional gas model. So hard gas model, hard loop. And last question, at the beginning of the class, I show you this pyramid of dimers. So it's pyramid of dimers, and now it's instead of pyramid of points on the square lattice, hexagonal lattice or triangular lattice, you can make pyramid of edges. This is pyramid of edges on the square lattice. So is it algebraic? This? So there is many problem of pyramid of something, of point or edges on the three lattice, triangular lattice, square lattice, hexagonal lattice. So is it algebraic derivative function? I don't know at all. Okay, thank you very much. So don't